8.1, we're finding the average value of a function on an interval. Question number 1 has this graph for us, and it says to explain why the area underneath the curve is more than 4 but less than 20. So if I look at this curve that looks quadratic, how do I know that the area underneath that curve going from x equals 0 to x equals 4 is greater than 4? Well, right away I can see that 1, 2, 3, 4, that area right there is 4, and I know the area entirely has got to be bigger than that. So I know it's bigger than 4. Likewise, if I found the area of this entire big rectangle right here, it is 4 times 5 or 20. The area of this entire region is 20. So I know it's got to be bigger than 4 and it's got to be less than 20. Rectangles are the easiest thing to find the area for, so I know that it's got to be between 4 and 20. Question number 2 says, do you know that it's more than 8? So I'll go back in here again. This area is 4. There's 5, 6, 7, 8. Those are perfect squares, so I know those areas are exactly 8. So I know it's still more than 8. If I'm saying, is it less than 16? Well, there's a width of 4. If the area is 16, the height would also be equal to 4. So I'm looking at this square right here. How do I think this area compares to the actual area in blue? Now, they have quite a bit of overlap. I'm really asking myself, do I think this excess area in this square, this 4 by 4 square, how does that compare to the part of that curve that didn't get counted? I think that there's probably more stuff that I'm counting here unnecessarily. Like I'm counting this and saying the area is 16. I think this is more than what wasn't counted. So I think that 16 isn't quite accurate. I think it's going to be something less than 16. Question 3 gets to the heart of the matter with this average value. At what height do you think we should draw a rectangle so its area is exactly the same as the area under the curve? So for this last one, I looked at the area under the curve, this blue region, and I compared it with the rectangle at the height of 4. I said that this rectangle or this square is too big of an area. So what I want you to do is draw in a different height. So it's not going to be a square this time. It's going to be a rectangle. The width of this rectangle is going to be 4. How high do you think, or what do you think is going to be the height of this rectangle so that the area of this rectangle is the area under that blue curve? So you're doing a little bit of approximating here. And everybody might guess a little bit different on this. Let's make it a quick 5-second or 10-second. Turn to your friend. What height did you choose so that the area of your rectangle is equal to the area of that? Okay, so again, we're estimating a little bit here. How many of you had your height bigger than 3? And we already said it was less than 4. Is it closer to 4 or is it closer to 3? Probably closer to 4, maybe 3.5, maybe a little bit above that. Maybe about right here. Oops. How about right here? So I'm looking at this saying the area of this red rectangle is about the same as the area of that blue curve. Like the parts that I'm including outside of the actual curve account for what didn't get counted in the actual curve. This is a ballpark. It says also in so my guess is about maybe 3.5, 3.6, 3.7, somewhere around there. It says in part 4, we're supposed to label this, or in question 3, label this height as C. So I've got an approximate number maybe I'm thinking of, but I'm just going to call this value C for right now. And then in 4A, it says write an expression that would give the area of this red rectangle in terms of this perfect height C. So if this height is C and the width is 4, then what is the area of that red rectangle? 4C. Part B, write an integral expression that gives the area under the curve. What can you say about this expression and the expression in question 4? Now this is called, the graph is called f of x. What would you do? Could you write an integral expression that would give the exact area of that blue region, the area under that curve? Quick turn to your friend. What do you think that expression is going to look like? So what would this look like? How about the integral of f of x? Is this enough information yet? No. What does it still need with it? The bounds from 0 to 4. What else does it still need? Dx, integrating with respect to x. So this would be the exact area under that curve. And then what can you say about this expression and the expression in question 4a? They're supposed to be equal to each other, right? So we're going to say that these two are going to be equal to each other. In question 5, we're given a little bit more information about this one. F of x looked like a quadratic. In fact, it is. It says f of x is negative x squared plus 4x plus 1. Well, we said the area under this curve is equal to 4 times c. Let's actually then integrate from 0 to 4 of negative x squared plus 4x plus 1. And we're going to set that equal to 4c. There's a couple of ways we could do this integral. Now, this integral isn't terrible. I could integrate piece by piece, take the integral of the first term, integral of the second term, integral of the third term. Because it is a definite integral, I don't need to put a plus c in there. I would take the upper bound minus the lower bound and get a definite answer for that one. Or, not a bad idea to use your calculator, good calculator practice. Go ahead and do that on your calculator then. Find this integral. We don't do a lot of work with the calculators. I assume you know how to do that, but it's not a bad idea to go back and check to make sure you really do know how to do that. So enter that into your calculator, find the value of that integral, which would represent the area under this curve, that blue region that I have highlighted up here. We thought, remember earlier, we said the area was definitely bigger than 4 and less than 20. Then we narrowed it down. We said it was definitely bigger than 8 and maybe a little bit less than 16. We said it was less than 16. We don't know how much less than 16, but that's kind of what we were expecting for that one. So you're finding the value of that integral on your calculator. It's nice if it comes out to a perfect integer. It doesn't, though, right? Did it come out to a nice fraction, though? Yeah. Like math frac, was it 44 over 3? Yeah. Okay, so take that integral on your calculator. 44 over 3 is the exact area under that curve. Remember, we set that equal to 4c. 4c represented the area of this rectangle. We wanted the area of this rectangle to be equal to the area under that curve. So if we set those equal to each other and now solve for c, divide both sides by 4, c is 11 over 3. 11 over 3. If you actually divided 11 over 3, what does that come out to? So 3.6 repeating, 3 2/3. Was that pretty close to the guess that we came up with? When I heard a lot of you give your guess, some of you said 3.75, I heard some 3.5s. Well, this is right in between there. 3 2/3 would be what it actually is, so that the area of the rectangle is equal to the area of that region. Question number 6 is the question that wraps it all up. How does the value of c compare to all of the values of the function f of x over the interval from 0 to 4? So if I were able to tell you, like a list of data, like if I told you like text messages, during this day, Alex got 20 text messages, Luke got 30 text messages, Jared got 0 text messages, Griffin got 1,000 text messages, and said, what is the average number of text messages those people received? I'd add them up and divide by 4. We can't really do this on a continuous function like this because there's no way I can get every single one of these y values off this graph if I'm looking for an average value. So what we do instead is a process like this. So how does c compare all the values of the function? C is the average of all the f of x values over the interval from 0 to 4. So we can use that integral, divide by the entire width to get the average value of all of them. Because there's no way we could actually find out all of them, divide by the number of terms that are there. It's continuous. There's no way to do that. This integral, this integral that was derived by using a limit as n approaches infinity, can average all those up for us. All right, so look at these important ideas. Go ahead and turn the page. Right, so we're talking about the average value of a continuous function. Is it important that this function is continuous? Absolutely. If it wasn't continuous, we couldn't integrate it. And we might have some issues with like some jump discontinuities and so forth. So the average value of a continuous function, parentheses in the right spot here, f of x on the interval a to b looking at this from a geometry perspective first. The average value of a continuous function on the interval from a to b is the height of the rectangle that encompasses the same area as the area under the curve. That's what we looked at on the front page. Let's make a more general drawing of that back here. So let's say we have a continuous function f of x. Maybe it's doing something kind of like this. And we're looking at this function f of x on the interval from x equals a to x equals b. So from this x value to that x value, I want to find the average output, the average y value, the average f of x of all of the f of x values that are in there. Again, it's a continuous function. There's no way we could actually find all of them and average them together. So what we do then is we integrate the function from a to b, find that total area under the curve. But then what do we have to multiply that by, or what do we divide it by? The entire width of the region. So we're dividing it by b minus a, which is the same thing as 1 over b minus a. Same thing, divided by that. That will give us our average value, the average height of all of those different y values for every single point that's in there. This is the average value. Now, tying it back to that geometry that I talked about before, I want you to estimate, can you put a C value in here where you think the average height or the average Y value is? Right? It's obviously not up this high. It's not down this low. It's going to be somewhere in between. So where you think the average height is, we'll call that C. And then I'll make a horizontal line. And what I'm saying is that I think that the area of this rectangle, using the average value, this C, is the same as the actual area under that gray curve. Average value. And not a terribly complex thing, but when it talks about average values, we've had average before. We've had average rate of change, AROC, which is something different. We're asking for an average value, not an average rate of change. So we have to make sure we read carefully. Again, it's a math class, but as you've seen, we've had a lot more word problems in this class, and you have to make sure you're reading carefully as you go into these problems. Number one, Chipotle gives buy one, get one burritos on Teacher Appreciation Day if you're willing to stand in line. On this particular day, the number of people waiting in line to order is modeled by W of T, where T is measured in hours since Chipotle opened at 11 a.m. Write an integral expression that would give the average number of people waiting in line at Chipotle from noon to 6 p.m. Integral. And I know it's an integral. I'm looking for an average value. The average number of people waiting at the line. It's the integral of what function? With respect to t. Now, if you actually did do this integral, there's more to it, but if you actually did this integral, what would the label on w of t be equal to? So that would be the people, and then the dt is hours. So it's people hours. And what kind of answer should we have for this one? People. So what would we have to divide it by? Hours. So I'm really paying attention to my label. I need to divide this by hours. Where do we divide it by hours at? The out front. Okay. 1 over what? 6. From noon to 6 p.m. is 6 hours. Now let's look at the bounds. We're going from noon to 6 p.m. Read carefully. So what's the lower bound here? 1, because noon is 1 hour after 11 a.m. And the upper bound? 7, because 6 p.m. is 7 hours after 11 a.m. So this would be the integral that would give us the average number of people waiting in line. Number 2, we're not going to use a calculator for this one. It says find the average value of the function on the interval from 1 to 3. So this one has no context to it. It is just straight up a function. Integral of, now if I was using my calculator, I wouldn't write down all this information. I just do g of x dx, save myself some time, make sure I didn't copy something wrong. But because we're not using the calculator, I am going to write everything in here. E to the 3x minus 3 minus 4x from 1 to 3. What else do we need with this? Dx. Also, we need 1 over 2. Why is it 1 over 2, not 1 over 3? Minus 1 is 2. That's the width of this region. Okay, so 1/2 integral of these two different parts, the e to the 3x minus 3 and the minus 4x, they're not multiplied by each other, so I'm not worried about like any kind of product. I'm just going to take those integrals separately. What is the integral of e to the 3x minus 3? It's not exactly e to the 3x minus 3. That would be close. Is the derivative of this equal to the yellow? What do you have to multiply by? 1/3. I could do a nice little u substitution, let u be equal to this, or let u be equal to my exponent, then du would be equal to 3 dx, so I'd have to multiply by 3, multiply by 1/3. The derivative of this is equal to what I want it to be. Again, I'm not showing as much work with some of these u substitutions. Hopefully you're able to do some of those in your head. More complex ones I still would, but I'm just kind of thinking backwards. The derivative of this would be equal to my yellow. Okay, what's the derivative of the blue? We're going from 1 to 3. Again, this is a non-calculator problem, so our final answer might look a little bit messy, which is fine. Equals 1/2. Let's plug 3 in our upper bound. So 3 times 3 is 9. 9 minus 3 is 6. So it's 1/3 e to the 6th minus, plug 3 in here, 2 times 3 squared. And notice I didn't do any of that simplifying. I'm not distributing the 1/2. I'm not even taking 3 squared times 2. I'm just saying plug it in minus, now plug in your lower bound of 1. That's 1/3 e to the 3 minus 3 e to the 0. I know that's 1. I'm just going to write e to the 0 minus 2 times 1 squared. I could simplify that to 2 if I wanted to. But my point I'm trying to emphasize here is this, for a free response question, is totally fine. All that's left in that is just a lot of arithmetic. Without a calculator, I couldn't give you a decimal answer because I have no idea what e to the 6th is equal to. I could do a lot of algebra to simplify this thing down. And maybe in a certain context, like if it's non-calculator, but if it's on multiple choice, they probably would have you simplify this down. But otherwise, I'd leave it right there. Some of you are in the habit of going further, which isn't bad, but there's a potential to make a mistake and definitely would take more time. So I'm good with this answer. Here is the average value of that function on the interval from 1 to 3. All right, number 3. In question 1, we work with some generic function w of t. In number 2, we work with a specific function g of x. We could actually integrate it. In number 3, we're given a table for some specific values, not an actual function, not an actual graph. And from this, we're asked to use a trapezoidal sum because I can't get a specific answer for this one. I'm going to have to approximate using some kind of method, a left or right or a midpoint Riemann sum. In this case, it's a trapezoid Riemann sum. If it helps, give yourself a quick graph. Can you set up what the trapezoid sum is going to look like? So you're estimating that integral using a trapezoid and then multiplying by 1 over 20. It's So let me pause for a second, give you a chance to do what you can do. Ask a friend for assistance if you'd like. Sum to approximate this value. I have my drawing over here, and then I have all of my calculations, or almost all of my calculations. This first trapezoid, I use my beginning height plus my ending height divided by 2 times the width of that region, and the width of this first one is going to be 4. My second trapezoid, I have my first height plus my second height divided by 2. I'm averaging those, but then this time I'm not multiplying by 4, I'm multiplying by 5 because that's the width of that region. The next region has a width of 6. The last region has a width of 5. So here is my calculation, and lots of numbers in there. I believe it comes out to 62.89. So B, using proper units, interpret your answer in part A in context. So if I look at the inside of all this, this would be degree minutes. And then we're multiplying by 1 over 20. And I know that that's what the case is because I have all those labels. We're multiplying by 1 over 20. The 1 over 20, it didn't give us any units, did it? And this is one of the things like about this formula that like I think math is usually very consistent and logical. Here's one of them that like you have to take a little bit of a, you have to like read into it a little bit. What is this 20 really referring to? 20 minutes. So you're dividing by minutes, even though it wasn't written in there. It's like an implied 1 over 20 minutes. So our answer should be degrees. What is this 62.89?
If a question like this popped up on the AP test and you got an answer that cleanly rounds to 2 decimal, or is cleanly at 2 decimal places, would you have to add a 0 just to show that you went to 3 decimal places? Or
no, this is showing how precise your answer is, so don't put an extra 0 on there. If you put a 0 on there, it's actually showing something a little different. So 62.89, and if you know that you're normally rounding to 3, you're saying it must be precise to this decimal point. If you did 62.890, then it's assuming that you rounded to 3 decimal places. So it's showing a different level of precision. It's also leaving the door open that like, hey, maybe it was 62.8897 and then round it up. So don't add that extra 0 if it doesn't need to be on there. Just like if an answer it comes out exactly to 15, don't call it 15.000, just call it 15. If there's more decimal, you can always go to more than 3 decimal places. If it's exact to fewer than 3 decimal places, go ahead and leave it that way. But you don't have to add a 0 to get up to 3 decimal places.